This is a video for AQA Discrete Mathematics. This is Linear Programming section 1.1, where we're going to look at how we formulate the linear programming problems. Now, by a linear programming problem, we're talking about some practical problem which has constraints. Quite often these are going to be to do with economics or maybe to do with production planning, and our constraints may be to do with time or raw materials or number of machines, etc., that are available. The fact that we're going to be looking just at linear inequalities, in other words those involving first power of x and y, no x squareds or square roots, means that our inequalities are linear functions, and therefore we get the term linear programming. In more complex programming you may have non-linear functions, but we're going to be looking at linear. Now, you can have a number of different variables, but we're going to be limiting ourselves to two, so just two different variables x and y. It's possible to have many different variables in a practical problem, and once we've formulated the problem, we will then go on in further videos to look at how we solve them. So once we've got our inequalities sorted out, then there's usually something that we need to either maximize or minimize. It might be profit or might be costs that we want to minimize. And maximizing or minimizing is referred to as optimization rather, and this is described by what's called an objective function. So we have an objective function which we would either be looking to maximize or to minimize. So the first stage in our formulation is to turn a wordy statement into algebraic functions. So we might have several variables. We're going to be looking at one to do with boxes in a second, but it could be quantities of different types of chocolates, and we'll look at that one a second. But it literally can be anything that we're looking at in terms of what the variables are, but mathematically we're going to assign these some algebraic letters. Usually we'll be using x, y and z if we're looking at three variables. And what we're trying to do then is to see how many of these variables we can make to achieve the aim of optimizing our objective function. I said later on we'll look at how we go about solving the problems for two variables, but now we're just formulating the problem and turning it from a wordy problem into algebraic formulae. So here's an example of a question. What you might want to do is to pause the video to just read through this, but I will work through it a bit at a time. But first of all, we've got a company that's making two types of boxes, and it says that type A box requires 4 seconds on the folding machine and 6 seconds on a stapling machine. We can make type B boxes which requires 2 seconds and 7 seconds respectively for that particular box. It says then we've got the idea that each machine is available for 1 hour. So we've got a stapling machine which is available for an hour, and a folding machine which is also available for 1 hour. So once we've decided those constraints, and it's going to be time constraints here, we've also then got an idea of the profit we can make. If we make type A, we get 40 pence profit, type B 30 pence profit. So the question is then, how many of each should we make to achieve our maximum profit? Well, the first thing was that each machine was available for 1 hour. The information about the boxes, however, was given in seconds, so we'll turn that 1 hour into 3,600 seconds. Now let's give our type A and type B boxes some letters. So we're going to let X be the number of type A boxes and Y be the number of type B. The first machine was a folding machine, and just taking the information from the question, type A boxes had 4 seconds on the folding machine and type B 2 seconds. So we can see that we have then a total of 4x. If we make x boxes of type A at 4 seconds each, then that's 4x seconds, and also 2y. So that's the total time on the folding machine. We've got 3,600 seconds available, so that total time must be less than or equal to 3,600. And of course that can be then simplified to 2x plus y is less than or equal to 1,800. The second machine was a stapling machine. And on the stapling machine, type A boxes require 6 seconds and B 7 seconds. So therefore we have that 6x plus 7y is less than or equal to 3,600. Nothing we can do to simplify that one, so that gives us our second constraint using the second machine. The other thing we need to do then is to look at our objective function, this time which is going to be to do with profit. And we've got 40 pence for type A, so the profit we would make if we make x type A would be 40x, and 30 pence for type B, so plus 30y. And we can say this is the amount of profit we would make in total if we make x type A and y type B. So our objective function P is going to be equal to 40x plus 30y. So our wordy problem then has turned into this. We need to maximize our objective function, P equals 40x plus 30y, with the following constraints. 2x plus y is less than or equal to 1,800. 6x plus 7y less than or equal to 3,600. So those are the two main constraints. We also, though, need to mention the fact that x and y are both greater than or equal to 0. We can't have a negative number of boxes being made. And because we're making things, it's also a case that x and y must be integers. So that's our problem turned from the words into algebraic statements, and we should just finish off by saying where x is the number of type A and y is the number of type B boxes. Sometimes there are some slightly more difficult type of constraints that we need to consider. So here's an example. Here we've got x is the number of milk chocolates and y dark chocolates. And the first question says there must be at least twice as many dark chocolates as milk chocolates. Now, some people get this the wrong way round. The way I sort of try and approach it is to say, look, if the dark chocolates are twice as many as the milk chocolates, then there must be more dark chocolate. So y is the bigger number. So y is at least, so greater than or equal to, 2 times x. So y is greater than or equal to 2x. Twice as many dark as there are milk. A different constraint would be a different problem this time. We've said that the dark chocolates must be less than 40% of the total number of chocolates. This one I tend to sort of do visually. So if you imagine a rectangle representing all of our chocolates, then the dark ones are the smaller bit at the bottom there, which as a maximum reaches 40%. Now 40% is 0.4. and the larger portion is going to be at the top, x, which, so in total we've got x plus y chocolates. So what this says is that y must be less than, y is less than 0.4 of the total, which is x plus y. Now you can then change that, of course, by multiplying throughout the bracket to give 0.4x and 0.4y, and then subtracting, so we get that 0.6y is less than 0.4x, or 6y is less than 4x. We might simplify that to 3y is less than 2x. But that's how to deal with these percentage type of constraints. Right, that's the end of the video on formulation of these problems. In the next videos we'll be looking at how we go about solving them once we've got the problem formulated.